Hi, ladies and gentlemen. Now that we have completed the two modules, now we are entering into the third module. The third module says about combinational circuits. So these are circuits which have no memory, and these are very fast in execution. So I will tell you the details of all those later on. In these combinational circuits, we have actually there are two kinds of digital circuits. One is a combinational circuits, that is without any memory or storage, and something called sequential circuits, that is with memory elements, broadly speaking. Now in this third module we see the combinational logic circuits, and in that combinational logic circuits we see first we see arithmetic circuits, and then we see circuits like multiplexers, demultiplexers, encoders, decoders, etc. So first we will discuss these arithmetic circuits. In these arithmetic circuits we see circuits for addition as well as for subtraction, as well as BCD addition, BCD subtraction, etc. So we will start by one. First we will discuss a half order circuit, then we will go into a full order circuit, then we will go into a block level treatment of the full order, maybe a 4-bit parallel order. Then based on that 4-bit parallel order we will make a BCD order. So based on these ideas we will go into subtraction circuits like binary subtraction, BCD subtraction, etc. So let me start with a half order circuit in this, and let me start with that presentation. So this speech is organized into your learning outcomes. Then what is a binary half order? What is the theory of addition with that? Then half order using integrated circuits like LSI or MSI chips, LSI chips. Then half order on verilog, and then summary of your learning. So what you will learn in this video is that you will learn the theory of binary addition with half order and design it. Then you will learn to implement the half order in QUCS and verilog. Then you will appreciate the wiring diagram for half order with ICs, with LSI chips. How do you implement on a breadboard or a PCB? So you have understood the basics of binary addition when we discussed it in the first module. That is, we add from left to right. See, we add the rightmost bit first. If it is a 1 and 1, you add that 1 and 1, and you get a sum as 0 and a carry as 1. So that when you add the second set of bits, say let us start with the rightmost bit as a 0th bit, then the first bit, etc. So if that is say 1 and 0, I add this 1 and 0 and add the previous carry to this. But if you look at the rightmost stage, there is no carry addition. Okay, there is no previous carry. So if you do addition with the decimal numbers also, you carry over the values, you add them. But if you look at the rightmost set of digits, there is no incoming carry, because there are only two numbers, you add them. There may be a carry generated, that is the output carry, that may be propagated to the left. But if you look at the rightmost term, whether it is binary or digital, there is no carry addition at that stage. You don't have to add any carry, you just add those two operands and you add them, you get a sum and a carry. So that rightmost thing, what happens is a half addition, because there is only addition of two numbers and no previous carry. So a half order adds two bits xn, say yn. That n denotes the stage of addition. If it is a rightmost one, I say it is a 0th stage of addition. There I add x0 and y0. In the next place, I have say x1 and y1. With x1 and y1, I add the previous carry, that is c0. Okay, but there is nothing like a c minus 1 there. I don't have a previous carry for the rightmost stage. What happens there is a half addition. So what it adds is, it adds the two numbers, binary numbers xn and yn, that produces some bit sn, say that is a nth stage output, and the carry output cn. This cn will go to the addition in the next stage. I will have xn plus 1, yn plus 1. I add them. Along with that, I add the cn also. Okay, so this carry propagates to the left as you proceed with the addition to the left. It does not receive any, this half order does not receive any input carry from any previous stage, because it happens at the rightmost stage, at the first stage of addition. If you take two binary numbers, you look at the LSB of that. When you add the two LSBs, there is no previous carry, because that is the starting point of the number. So there, what I perform is a half addition, just the addition of two numbers alone. In other cases, you do a full addition, that is addition of two numbers plus the carry from the previous stage. So the truth table of a half order looks like this. I have two inputs, say xn and yn. It may have it has combination like 0 0 0 1 1 0 1 1. Now what happens to this sum? What is the sum? If you add them up, I get 0 plus 0 is a 0, carry is a 0 because it is just a 0 and no carry. 0 plus 1 value is a 1 and the carry is a 0. 1 plus 0 is a 1 with the carry 0, and 1 plus 1, it is 0 with the carry 1. It is basically 1 plus 1 is 1 0 because so that means the sum bit is a 0 and the carry generated is a 1. So if I have a next stage of addition, say xn plus 1 yn plus 1, what happens is this carry will propagate to that. I will add this carry with the values xn plus 1 and yn plus 1. So if you look closely into this thing, you can see that Sn is a XOR b, xn XOR yn. Sn is an XOR function. If you look at it, it's the same truth table as that of an exclusive OR gate. So it is Sn is xn exclusive OR yn, and Cn is nothing but a time xn times yn because it is 1 here. So the term is xn and yn. Now you can see that Sn, the sum bit is xn exclusive OR yn, and the carry generated there at the end stage, that is xn and yn. Okay. Now the circuit, end the stage of addition circuit, half order circuit, that looks like this. Xn and yn are the inputs. I add them, I get it's an exclusive OR operation. I get Sn, and these are ANDed to get my carry. This carry goes to the next stage of addition. Half addition or half order comes only in the rightmost bit. So when you add the L to LSBs, this half addition happens. So I can do the simulation in QUCS. I will take that in QUCS. Now I have a half order circuit here. I will open in this terminal. I type QUCS. I open this half order. I have ha.sch. It's a half order circuit. I will enhance it a little. Now you can see that these two bits are coming here. Here I put this is my exclusive OR gate. This is my xn and this is my yn. Xn is my LSB with one number and yn is another number. Now here I connect xn to a signal source, that is 1 nanosecond 1 nanosecond, and this is to 2 nanosecond 2 nanosecond to make the truth table interesting. This is 2 nanosecond 2 nanosecond, and this is the sum output. Here is my sum output, and this is my carry output. Okay. If I perform a simulation, you can see these signals. You can see that initially xn is xn and yn is 0 0, Sn is 0, Cn is 0. When it is 0 1, this is 1, Sn is 1 and Cn is 0. It is 1 0, Sn is 1 and Cn is 0. And when it is 1 1, when xn and yn are 1 1, it becomes Sn is a 0 and Cn is a 1. Okay. Now you can appreciate the truth table also. I will take xn, yn, Sn and Cn. When it is otherwise I'll put in the actual other order so that it will be quite consistent with what you learned. I will take yn first. yn is there, xn is there, sn is there, cn is there. I apply OK. Here it is yn is 0 0, sn is 0, cn is 0, yn is 0 1, yn xn 0 1. It is sum is 1, carry is 0. It is 1 0, the sum is 1, carry is a 0. When both are ones, sum is a 0 and the carry is a 1. Okay, this is how I simulate. And one interesting thing here is this thing. I have designed two ports here. The output is put as a port. This we didn't see so far. So one advantage is when you declare these ports, I can use this half adder as a sub-circuit. I will come to you that later on. So this is a port. This is actually a sub-circuit. This sub-circuit. So I can make one circuit, one big circuit, and I can convert that to a sub-circuit and keep it as a block in other circuits. I will tell you that when we discuss the 4-bit parallel ladder. I will tell you that. Now let me go back to my presentation. Now if you want to connect on board, suppose you have a breadboard and integrated circuits, like I have what I need to implement the half adder, an XOR gate and an AND gate. Okay, an XOR gate is 7486 or 74LS86 or 74H86 or something like that. I generally call it 7486. And AND gate, that is 7408 AND. So what I do is I connect these two things on the breadboard, connect the 7th pin to ground. First you have to connect these pins to ground, 7th pin to ground. Then you connect this 14th pin to VCC. Okay. Then connect at the this 7486 should be wired to get the sum bit. So here I apply in one of these gates. I applied here in 13 and 12. I applied x and y, xn and yn, so that its sum sn comes at this output. There I connect an LED, and normally on LED, so that whenever this output is low, this LED glows. Okay, when the output is high, the LED does not glow. Now I have to, with this I obtain my sum expression. Now I have to have the carry, that which is nothing but xn and yn. So for that I use the 7408. I connect to supply ground. Then I choose one of these gates, one of the 4 gates. Here I chose 12 and 13. Okay, here 14 is connected to VCC, 13 and 12 are connected to x and y. Okay, so this output is my CN, that is connected to an LED, a normally on LED. So when the output is low, the LED glows. When the output is high, the LED does not glow. So with this, you can apply this pattern 0 0 by connecting this to the supply, alternative to this supply, like 0 0 0 1 1 0 1 1. You can you can verify the truth table with the help of this circuit. Okay, hopefully when you come to the lab, you can try such circuits. So this is a wiring diagram. So you appreciated the wiring diagram. Then I have to do this half adder on verilog. So if I want to do it on verilog, the code looks like this. The verilog module, like the gate level verilog module for a half adder looks like this. Suppose I start with a module n module, and I give some name, half adder, h adder. Output I have two outputs. They are wires, which are this, the sum and the present carry. Sum output and the carry output, that is Sn and Cn. Then two inputs are there, inputs wire xy I say. Okay, so this is my sum output, that's an XOR function, give some name n1. Okay, its output is sum, inputs are x and y. And the carry output is generated by this AND gate, that is AND into some name. Output is a carry, comma, inputs are x and y. This creates your verilog half adder. Now I'll run this code for you. Here you can appreciate that code. This is my half adder. Okay. Here I open another terminal. I type verilog. I will make it a little bigger. Verilog. verilog h order dot v. Now it is compiled without any problem. Now I have to look into the test bench. The test bench look like this. What I need is I have to grave include hrr.v. This is my unit under test or device under test hrr.v, the one I just compiled. Then module test benches, then reg xy, wire sum carry. These are outputs. Sum and carry are outputs. These are my inputs. I go through registers. Now I take an instance of the half order here, h order y1, say some name, some carry are the inputs, comma x, comma y. Now initial I monitor time, everything is as in the previous case. Some carry are binary, some carry x, y, they are binary values, 1-bit binary values. Now I dump this to hrr.vcd. Now here I give these patterns for every 5 units of time. I give 0, 0. Yeah, here I will give, these are all the same. 0, 0, I will put a 0, 1. Okay, I can put this a 1, 0. And 1, 1. Now you can run this code. I will specify some output file a.out. I will run this a.out, a./a.out. You can see that at 10 second this x is 0, y is 0, so carry is 0, sum is 0. When it is 0, 1, sum is 1, carry is 1. When 1, 0, carry is 0, sum is 1. When 1, 1, xy is 1, 1, sum is 0 and the carry is 1. Now you can appreciate these waveforms just like the waveforms we saw in QUCS, GTK wave, what is it, hrr.vcd, correct, hrr.vcd. Now you can take these values, I can expand this a little. I will add these things like I will take x, y, then I will take my sum and carry. You can see these signals. This is very initially for 5 seconds. For the first 10 seconds it remains an ambiguous state, and then that's the time for a kind of a global reset. Now I will zoom this. You can see that initially it is 0, 0, the sum is 0, the sum is here, sum is 0, carry is 0. When it is 0 and 1, sum is 1, carry is 0. When it is 1, 0, the sum is 1, carry is 0. And when it is 1, 1, the sum is 0, carry is 0. Carry is the third line, carry is 1. Okay, so this is how I develop a test bench for the verilog module for half order. Now let me again go back to the presentation. So what you learned in this video is that you learned the theory of binary addition with half order, and you designed it. You learned to implement this half order in QUCS and verilog. Then you understood the wiring diagram for half order with the integrated circuits. And that is the end of this video. I thank you all.